Well, good afternoon and welcome to this month's Perfect Practice webinar, Datrium, a new category in healthcare data storage. I'm your moderator for today's event, Nancy Roberts. This webinar is presented to you by National Physician Services, a charter member of the Perfect Practice Alliance. Our agenda for today is one we think you're going to find of enormous importance to your information technology strategy. We'll begin with a quick introduction to National Physician Services, and then we'll talk a little bit about NPS's newest partner and guest today, Datrium, and then we'll move right into today's webinar topic as Brian Biles, CEO and founder of Datrium, explains how a breakthrough in data storage technology can benefit your organization. And finally, we'll take any questions that you may have at the end of the presentation. So we'll start with a quick overview of our host, National Physician Services, or NPS. NPS was founded by physicians and healthcare technology visionaries to provide innovative solutions for hospitals and medical practices across the country. They provide an end-to-end suite of healthcare information technology services, from CIO advisory consulting to disaster recovery planning, application support, and desktop services, all the way to comprehensive managed IT partnerships. For information on NPS, visit our website at nationalphysicianservices.com. Now, in keeping with our goal of bringing you the latest in healthcare technology innovation to drive efficiency and lower costs, we want to introduce our newest partner, Datrium. We understand that one of the greatest challenges looming over healthcare IT is how to manage the ever-growing volume and complexity of big data. Healthcare providers must be able to flexibly and efficiently handle more and more information at lower costs in order to succeed. In our relationship as a value-added reseller of Datrium solutions, we're very excited to be the first company to bring this game-changing technology to the healthcare market segment, and we believe we've found a partner that is literally setting the bar in healthcare data storage. As you can see from the quotes on your screen, both Brian Graven, CEO of NPS, and Brian Biles, CEO of Datrium, are very enthusiastic about this new relationship and the value it brings to the market. Now, we want to be sure that we not only share the Datrium story with you, but that you also get an opportunity to ask the questions that you'd like to have answered. So to ask a question electronically, you just locate the Questions tab here in your control panel, expand it, and type in your question, and we'll address it as soon as we can. And of course, we have our regular planned Q&A session when we wrap up the webinar today. And now we are very pleased and proud to introduce Brian Biles, CEO of Datrium. An industry innovator, Brian has worked with some of the biggest names in technology, like Sun Microsystems, EMC, and VMware. And today he brings that knowledge and experience to this event as he introduces our presentation, Datrium, a new category in healthcare data storage. Brian?
Thank you so much. And thank you everyone for attending today. Before we get started on Datrium and the product that we're bringing to market with NPS, I wanted to spend just a minute giving a little bit of background about the people behind Datrium and kind of how we ended up where we are. About half of our founding team came from a company called Data Domain, which you may have used in the past. It's a leading product in deduplication and backup. I was a founder there, and our CTO and his lieutenant CTO started this company. We also joined with two guys who were of the top, say, dozen sort of VP level engineers at VMware early on. And you'll see as we get through the product why this particular chemistry was so important. When we looked at the next wave of infrastructure going in modern data centers, there was a clear pattern a couple of years ago with the advantages of virtualization and commoditization of servers with networks getting faster. What used to be an effort to try to offload servers from whatever was possible has actually kind of gone the other way, and people are trying to onload more and more of the capability that have been in appliances or in sort of separate containers. You can see this in a lot of areas of the data center. In databases, things are moving more and more to in-memory databases where the reads are all within the host, and it still writes to an off-host replica for safety. But you can see this in SAP and Oracle. The same thing in network products. There's a move to do more and more of the control of the network in scalable server infrastructure using available CPUs and not put it in bigger and bigger appliances. We figured this was likely to happen in storage, and there was one particular thing that was causing it to happen, and that is flash storage drives. Flash has had a huge impact in the storage industry. In every kind of array now, you can get either a partially flash or all flash version of that kind of store. What's happened though is sort of independently, those components are available on servers at a much lower cost. And it turns out many of you may be using them already. Not only are they lower cost, as you can see on the left, compared to array flash, they also end up performing better. On the right, it shows as you add more cores and you add more VMs to a host, the more simultaneous requests for I/O reflected by the thing on the bottom, the queue depth, how many requests are being made at the same time. The more of those that happens on a server, the more the SAN is going to get in the way. And this is shown on the right chart. With latency increasing, the more there are outstanding requests. So even if an all-flash array could have sub-millisecond response time, as the number of cores increases, you can't get to it. So it actually, not only is it a lot more expensive to get flash in an array, it also just doesn't perform as well. So Datrium set out to solve this, and in particular for VM storage, which is now approaching 80% of all the workloads in the enterprise, with a very different approach that allows us to scale speed independently of capacity and take full advantage of these emerging trends in pricing. Another alternative, just to compare, is what's called hyperconverged infrastructure. This is an approach where everything is bundled together, where you scale everything together at the same time. There's some, every major server company offers this now, and there are a couple of well-known startups doing it. In effect, it is an array that also runs VMs. Every node does a combination of VM workloads as well as storage. And so it has some of the side effects of an array. If a host goes down, it increases data risk just as it would in a scale-out array node. The bandwidth that goes from host to host is different from a SAN. So, usually in a SAN, hosts don't talk to each other that much. If you do more of that, the scaling leads to a network replan. Quality of service and troubleshooting are all sort of, overpooled, so it's complicated. There's a lot of neighbor noise. And it's just sort of a rigid configuration. You have to rip and replace existing infrastructure to put it in. It doesn't work with existing infrastructure. And you can't upgrade speed alone. So it's unlike things you're used to with a SAN. We felt there must be a different way to go. So in our model, we've split speed and capacity. We've split speed from data durability. This chart shows the way that we're building our product. The box on the bottom is the thing that we ship when we install our system. It looks sort of like an array, and mechanically it's sort of like an array. It has dual controllers for HA. It has battery-backed RAM for fast, durable writes. And it's where all of the write replicas go for persistence. But we've separated that from all the stuff that you normally think of an array doing for data services, like RAID and dedupe and compression and snapshots and clones. All of that stuff has been moved to the host. And we start by expecting that you've added an SSD or two to every host, because every server vendor sells them now. They're widely available as commodities, and they're pretty mature. So both the CPU speed that's normally in an array controller and the flash drives are server components that you buy from your server vendor, where they're actually a lot cheaper than buying from an array. And by doing that, all of the read I/O can be local. So you can use these very fast commodity flash drives to read all of the data that you normally look to an array to provide. We support that as a very large cache. As you add hosts, you add speed. What we upload after we've done an install of our system is a piece of software we call a hyperdriver. And it does all the things that you'd expect array software to do. We just use sort of remaining host cycles to do it. There are an unlimited number of licenses for this included in our net shelf. We support up to 32 simultaneous hosts today. So by splitting this way, it's very different from a normal array. It's different from the sort of scale-out array with also running VMs that a hyperconverged model might apply. And it means the most expensive parts of the storage system are things that you buy independent of us, the flash and the compute. We take care of the software and the durable data. This has a number of really important effects. So what I'll go through next are just a little bit of explanation of these points. By doing it this way, first, the system is faster than all flash arrays. And this actually gets faster as you add hosts. It's maybe the first storage system that has ever had that effect. Second, because we don't sell the expensive parts of what would normally be in an array, it's about half the dollars per gigabyte of what are called hybrid arrays, the sort of cost-efficient arrays that are on the market today. And finally, it's more flexible than hyperconverged systems because you can use your existing infrastructure. Any kind of server that you currently have has enough drive bays to run a cache. And it gives, in our model, a lot of isolation and locality architecturally, so it's easy to troubleshoot, easy to scale. So first to the topic of faster than an all-flash array, this chart shows what happens to the aggregate IOs per second in 32 KB IOs as we add hosts. I'll explain at the end how we have a lot of isolation and locality of IOs per host, but as you add hosts, it adds speed, and that's independent of how much you've actually stored. This also shows one of the knobs you have for optimization of quality of service. Because we use host cycles, if the hosts are faster with different clock speeds, or you apply more cores, it's a host with more cores, it actually produces more speed as you add the number of cores and clock rate. A typical all-flash array controller is shown in the red line at the bottom. So you can see how, if read speed is your interest, this is a very simple model to scale. But we make it also a little better in a different way. There are other techniques to modify speed dynamically. One is just coming out right now, and that's a software switch we'll demonstrate at the end of this discussion. Normal deployments, our sort of normal default is we use 20% of a host's cores for processing storage. With a software change, you can hit a button, it can go into what we call insane mode, where it uses 40% of a host's cores. The chart on the right shows what happens when you do that, and this is showing both 4K and 32K IOs. The dotted line is our default, the solid line is what happens when you push the button. So you can see with a very dynamic change, you can get enormous I/O rates from just a conventional x86 host, over 100,000 IOPS per host. Another mode, or another method to change speed dynamically is shown here. Just as background, the bullets on the left describe the various ways that we are VM-centric. So per VM administration end-to-end, there aren't any LUNs. It's all the management is through vCenter. Clones are offloaded through VAI, and so on. The picture is what I wanted to highlight. If you have multiple hosts and one has VMs that are getting a little crowded. The SLAs are turning out to be hard to meet. With an array infrastructure, at that point, you would pretty much have to call the array vendor, order an upgrade, and tens of thousands of dollars later, with a new controller and maybe some new flash, you might get faster. In this model, all you have to do is vMotion that VM to an adjacent host that has a little more resource headroom. It's, again, a dynamic effect, much better suited to the mobility of workloads and the dynamism of today's IT departments. So the net effect is what's shown here. As you add hosts in a DVX model, you can add resources for speed, and so speed per host can remain consistent. As you add hosts in an array model, you divide the performance resources that are in that system. So performance per host actually declines. If you're in a dynamic IT data center, this is a very useful effect to take advantage of. And as I said, even with this line, if you decide to either increase performance within a host or use mobility to get access to resources in a different host, we make that very easy. So that was talking about how we're faster than an all-flash array. That wouldn't be interesting if we were more expensive than an all-flash array. In fact, all-flash arrays are pretty expensive. The cheaper kind of array that you can buy today is called a hybrid array, where it uses a little bit of flash and a lot of disk. And there are some really good vendors that do that with modern designs. I've shown two here, comparisons to a current Nimble storage product and a TinTree storage product that are well-regarded hybrid storage arrays. When you compare the price of a Datrium DVX, it's about half of what you'd expect to pay for those systems on a dollars per gig basis. And the reason is the bullets on the right. First, we use underutilized host compute and host flash. Flash is, as I showed before, about almost an order of magnitude delta in price for the same capacity. And finally, in our model, because of the data domain background of the founders, we have built in deduplication onto all layers of our system, including the back-end disk system, where most hybrid arrays don't have that, or else they make it a selectable option that has a lot of overhead. In our case, we built it in from the beginning, so it's very efficient. The final point I wanted to talk about technically that separates us from a lot of the rest of the market is isolation and locality. And these are a little, kind of big words to explain a pretty simple thing. In a model that pools everything, like the hyper-converged style that's emerging, it's very hard to troubleshoot because everything's kind of melded together. So if you have a problem, it's pretty hard to isolate it. And also on locality, we put flash and CPU for a given workload from a storage processing standpoint on the same server that the workload is. So we don't reach across hosts to try to steal cycles from others, because that also makes quality of service and troubleshooting hard. The first point on the bottom is we isolate system and data failures from each other. In this model, all the writes go to the net shelf, the box on the bottom. So if all the hosts failed simultaneously, the data would always be safe. That's different from a more pooled model, hyperconverged model, where any host that fails is actually a scale-out array node. So you lose some data fault tolerance in doing that. It has to start doing a data rebuild. The second thing is our software that runs on the host runs on the ESX kernel, not in it. So if our software has a failure mode of some kind, access on that host to our storage would be affected, but the host keeps running. So if it's mounting other data stores, no problem. The final thing is, kind of the heart of the performance question. All of the hosts either work with their own resources or work with the net shelf. They don't talk to each other. And that means you don't have neighbor noise directly affecting other hosts when one host is trying to write data. They basically just work independently. That locality means you can resource hosts or host clusters specifically to get a particular quality of service or service level. It also means as we scale, the provisioning of network bandwidth is much more like a SAN rather than host-to-host traffic, where you'd need to consider a leaf spine network as you scale. So again, just to wrap, it's a different kind of model. We've split speed and capacity speed from data durability in a new way, but it's in a way that's very friendly to the trends that are happening in every other part of the data center infrastructure. And it allows this kind of system to be faster than all flash arrays, half the dollars per gigabyte of hybrid arrays, and a lot more flexible than a hyperconverged model. Hopefully that was clear. I wanted to pass the baton at this point to Mike McLaughlin, one of our senior technical people who can show a demonstration of how the product works.
Okay, thanks, Brian. We have a demo video here that we put together that I hope is going to help highlight some points that Brian just made. And as we get into this, I'm going to be pausing to make sure that it's streaming to your desktop appropriately, and also making the points that we have here. So maybe for the next 7 to 10 minutes, we're going to walk through essentially a video of the product here. 3 key points I want to make sure we can highlight from what we just heard is the Datrium solution brings scalability and flexibility by adding hosts, by moving workloads with something natural to VM administrators like vMotion, and also by adding servers and the core count in those. So as we're taking CPU resources to run our product, the server configuration is important, and we'll see that. And then also this last little bit that we showed here, which was the fast and sane mode, giving the operator some additional controls over how things actually run on each host. So with that, we're essentially going to start with a single ESX host that has some workloads on it. And I'm going to move these workloads to other hosts and switch them into insane mode. And through this demo, we're going to basically see the system go from a beginning of about 30,000 IOPS to an end of somewhere over 200,000 IOPS by deploying core, servers, and insane mode. All right, so the 2 hosts that I have right now, I'm going to pause here for a moment. 2 of them have 20 core. These are pretty standard run-of-the-mill ESX hosts. I have one that has 32 core in it as well. That will give us a little bit more horsepower. And as I push these into insane mode, the horsepower or the utilization will go up. And we should get to the end here where we go roughly from 30,000 to 200,000 IOPS in this demo here. So bear with me as we sort of dive into to our vCenter environment and take a look at this. So we start off in vCenter. Everything we do in the Datrium product is organized through a vCenter plugin. So we're going to bring up the DVX dashboard and basically look at the top level view of our system. And this is our host running roughly about 30,000 I/O. We see the total throughput of the system. Now these are all the VMs on Datrium storage. We can see the DAVG latency, which is fairly high right now, and then we're going to address that before we get through with this demo, because I've basically crowded a bunch of workload on a single host. And I did that mainly for the amusement of this demo, and we're going to try to resolve that here. But you can see that I'm getting 100% cache hit also on my local flash that is on these hosts, and that's a good thing. All right, so let's drill into the host itself. And we see here we have these 3 hosts. One of them, the top one here, is fairly busy. He's running the 30,000 I/O. The 2 below it are idle right now. We're going to take advantage of that. But first, let's drill into this host. And hopefully this is all showing up on your screen. Very good. Okay, so here's the 30,000 IOPS on this one host. And we notice over here in the upper right, it's in fast mode. Brian already talked about going insane. So let's click that little button there and see what happens when we go from 20% to 40% CPU allocation on this host alone. All right, we can do this on the fly, live on an ESX host, without, this is essentially the only storage operation that I'm doing today, is everything else is being managed through the virtual center, through the way a virtual administrator would manage his virtual machines and applications. But here I've chosen to go insane, and we can see that our IOPS have, I guess they're about double. They went up to mid-60s now. Let's top back up to the the high-level view, and we can see that we actually have 66,000 IOPS, but we're still running on a single host. Well, I have 2 more hosts available, so let's take one of the Datrium premises here and distribute the workload. So I'm going to go to my virtual machines here, and we can see that they're all running on that single ESX01. So I'm going to grab the workload here on the second host, and I'm going to migrate that to another ESX host in my cluster. And it's literally about this simple. A couple of next buttons. The virtual machine will now migrate to ESX2. And for those that are paying attention, I'm going to have a little background quiz for yourself. What do you think the IOPS will be when I go back to the top level? All right. I know what the answer is, but we're going to see if it makes sense. We should be seeing about another 30,000 IOPS from that host. So we went from 30 to 60. We're now at 90. All right. I still have flexibility. I still have scalability. I still have administration control. I'm going to go insane. All right. I'm going to go to the second host here, which we see is running about half as fast as the first host, and that's because he's in the fast mode. If we click insane here, we can now bring more CPU power to the storage problem, and the workload on this host should now roughly double and get into the 60s as well. All right, give this just a moment, and this is not a transmission problem if your screen should shake here. But we're now in insane mode, and we're going to basically see what it looks like at the very top. Go back to the high-level view of my 3 hosts in this cluster. We're now cruising along at about 130,000 random IOPS. All right. I said we could continue scalability. I still have a third host here. If you remember, this one actually had 32 core on it, a little bit beefier than the 20 core systems. So I'm actually going to vMotion 2 virtual machines out of my original inventory onto that host. This will just take a moment as we click through. I probably could have done both of these in one vMotion pass, but I'm essentially moving both of these last 2 virtual machines onto the third host so that I can now distribute the workload across 3 hosts in my cluster. I'm basically getting server-powered storage times at least 3 from where I started. Okay, let's give a moment here while this finishes up the vMotion to this third host. And I'm going to tell you now, this one is only in fast mode. All right, I saved the insane mode button for the end, but now we're basically distributed our workload. We have 1 VM on the first host, 1 on the second host, and I've pushed 2 onto this third host, which has more core. So we have scalability through server selection. All right, so as you're out procuring new hardware, you can think about how much core you want to bring to bear for the application or the storage performance. Now that's only 195,000 IOPS. I think at the very beginning I said we'd get to over 200,000. From 30 to 200,000, well, it blipped there for just a second if you caught that. But we can see here that my 2 hosts running in insane mode with 20 core are about the same as my heavyweight host in fast mode. But if I click this into insane mode, we should get nearly 100,000 IOPS out of this box. All right, and this goes back to that graph that Brian showed a little bit earlier of the scalability of random I/O on a single host and with small block I/O. And 99, that's probably good for now. Let's take a look at the top of what we're looking at here. The 3 hosts, aggregate performance, aggregate throughput, and what do we have? 237,000 I/O. Now, I want to point out something here. That DAV-G latency in the third window here was close to 4 milliseconds for those 4 virtual machines that were crowded on that one host running in only fast mode. That was probably still okay. But through the Datrium solution, we were able to scale by adding hosts with more core, and move them into insane mode, and literally dropped our latency an order of magnitude on that workload. And we did that basically all managing this within vCenter, and as we would manage our virtual machines. And the only storage-related button that we really had to worry about was fast or insane. And here we can see where the end and what our virtual machines look like spread out across a well-balanced cluster. And that's kind of the end of this online demo. There's a lot more detail behind the scenes. I recommend contacting someone with this particular WebEx if you'd like more information. But that's it. Thanks, Brian. And Brian?
Thanks, Mike.
All right.
So at this point, I think we can open it up for questions. Is that right?
Yes, we can. We will do exactly that. That was sort of the equivalent of watching a superhero movie in of data storage. That was pretty astounding demonstration. We did get some questions. I think people were pretty much entranced, and they came in here. First question was, what gets installed on the host?
Oh, great question. So this is Brian. We have, before we bring a system in, we go through a checklist of just making sure everything's set up, beforehand. And part of that is making sure that, there's at least one SSD per host. The SSDs need to add up to at least 800 gig, and, you can do up to 8 terabytes of local SSD if you want. Once we install our system, we go through an load process where we upload a piece of software called a hyperdriver to run on ESX in each of those hosts.
So now, does that address the second question, which was, are there limits to how much flash, SSD, or hosts that can be deployed, and what's the cost associated?
Yeah, we don't sell and support the flash directly. We assume that you get that from your server provider, but it's, again, 800 gig to 8 terabytes physical flash. That can be, we have a sort of compatibility list, but it's all the leading vendors, and it can be either SAS or, SATA drives up to PCIe and NVMe drives.
Okay, and how much, this is obviously a good question here, how much of the host is used for the hyperdriver, that is the Datrium software?
Good question. As we noted in the demo, in the slides, from a CPU standpoint, we reserve by default 20% of the CPU for the hyperdriver, and if that's mode, it'll reserve 40% in insane mode. A reservation means, we'll have sort of rights to it in a conflict if there's a fight between VM use and our use, but if we don't need it, VMs take it, and life goes on. The normal VM CPU utilization worldwide is about 30 or 35%. So usually this is pretty easy to accommodate. From a RAM standpoint, it's a little less than 10 gigabytes of RAM to get started, and then it's a gigabyte for every terabyte of flash that you add.
Where is this data reduction, the dedupe and compression, where is that performed?
Yeah, good question. Like all of the data services operations, it's performed on the host, and that's within the minimum core count that we recommend.
Okay, and one final question here. How is DVX different from HCI?
Yeah, I had a slide on that earlier. HCI is the acronym for hyperconverged. A hyperconverged model is, first of all, converged. So it's a complete sort of pod of infrastructure, servers and storage, where a DVX, Datrium approach supports existing infrastructure. So we can use any kind of host, any kind of server, blade server, quad socket server, whatever. The second, the hyperconverged model is as I sort of described, it's like a scale-out array that's also running VMs. So it's putting all of the same I/O and all of the same compute onto the one box. It's like an array box. So if in a scale-out array, if one node fails, then you have to do a rebuild, and that's similar to hyperconverged. You have a lot of host-to-host I/O traffic, which we don't have. You have all the things that you normally think about with array rigidity and inflexibility on configuration. It's the same thing with hyperconverged. You can only get certain models. You can only upgrade them to a certain extent. So it's a much more restrictive format. The DVX is aiming at existing infrastructure, the full spectrum of server options, and a lot more kind of SAN-like network build-up.
Well, great. That was the the questions that came in, but something tells me there will be more to follow. It's a complex and fascinating subject, and thank you very much, Brian and Mike, for your presentation. Thank you all for being here with us today, and if you have further questions, I'm sure you do, or you'd like to set up a brief introductory call to review your current data storage environment and your ongoing needs, please contact Tony Cincagrono at National Physician Services using the phone number or the email address you see on your screen now. And we want to thank all of you, our presenters, as well as our attendees for being with us today. We look forward to hosting you again at an upcoming Perfect Practice Alliance webinar. Everybody have a great afternoon.